Thanks, Tridge. So this is an update on the Gazebo simulation, and there've been quite a few changes to Gazebo over the past couple of years, and so we've managed to incorporate most of those changes into our integration with ArduPilot through CIDL, and this is a run through what we've done to make ArduPilot work with the latest version of Gazebo, and then a walk through some examples. So the outline for the talk is kind of a review of what's new, then the changes that we've made to the plugin and some enhancements there to add some extra features to take advantage of some of the new things in Gazebo. A couple of tools that are kind of not integrated necessarily with the ArduPilot stack, but that I find quite useful for working with the new tools from Gazebo, and then some next steps. And then on the second part, a review of some of the models that we've made available and ported over to the new version, and then a case study, which is a sailboat simulation, which is really where I got started with the ArduPilot work a couple of years ago, when Pete Hall asked if we could take some of the work I'd been doing on wave simulation and apply it to the work he'd done on sailboats originally. So we'll have a look at that towards the end. So Gazebo has undergone quite a big change from its first version, which was used with ROS 1, to its current incarnation. It's gone through a few name changes, but they're back to Gazebo now. And it's shifted from being a fairly monolithic application into a customizable toolbox of simulation libraries and other features. And pretty much everything around the environment is customizable now. So it's written as a series of about 9 or 10 different core libraries. And each of those is arranged as, well, most of them are arranged as sort of pluggable. So the simulation physics backends, the rendering engines, the sensor plugins, each of those can be swapped out for a different backend, and the Gazebo team provide defaults for all of them. But if you want to, you can replace the entire physics backend with another sort of 3D physics system. So it's using Dart now as a backend, which is fairly solid physics, sort of rigid body engine. The big change on the rendering, it's improved quite significantly over the earlier version. So Ogre is the render engine that they use. There's a new version of that which supports physically based rendering. So the lighting and shading is quite fancy now. And some of the demos which I've put up there on the screen are from shots that the Gazebo team have put out with various releases that they've done. The sensor system is quite a lot more advanced than it was before. It's much easier to add custom sensors. It used to be quite difficult. They've got a fairly rich camera system that comes along with the improved rendering engine. So there's things like there's the standard RGB cameras, but also depth cameras, thermal cameras, stereo cameras, as well as things like segmentation cameras for chopping up pictures into boxes for AI analysis. The simulation engine has been really reworked, and it's more designed now like a game engine. They use this entity component system, which is quite abstract, but it allows you to extend the system with plugins probably a lot easier than before. So all the features, all the simulatable features are attached as components to entities within the system. So everything that you might think of as an object within the simulation is just an entity. It's given an identifier, and then its behaviors are modified by attaching features to it. So something that is a link or a model in the library, you attach things that might be interesting physically to it, like it might have a pose, it might have a velocity, it has the ability to be subjected to forces and things like that. So depending on how you want an entity to behave, you just attach components to them at runtime. and that makes it very, very flexible to work with. And so the system can be as lightweight as you like, or you can add quite a lot of complexity to an individual entity within the system. The GUI itself, it's Qt based, and again, you can add Qt widgets as plugins. So if you've got, and we'll look at that a little bit later, it has a bridge to ROS and ROS2. So this is it's called ROS-GZ. I won't go into that too much, but I think that's going to become probably increasingly interesting with some of the work that has been done with the ROS integration into ArduPilot. So we'd probably be looking at using Gazebo as a simulator for that, and the bridge from ROS2 into Gazebo will be handy for that. So on the plugins, quick overview of what we're looking at. There's the kind of migration from Gazebo Classic, as they call it now, to Gazebo Garden, which is the current released version. We provided we swapped out the old interface for a JSON interface. There'd be some changes into the types of commands that you can configure in the controllers. And then there's some extra features where we've kind of added things like parachutes and gimbals and some extra sensors. So we'll cover those. The original port from Gazebo Classic to Garden, it was done by one of the Open Source Robotics Foundation's people, Brian Gerke, who did that for a version Gazebo 3. And this was a migration of Pierre's original ArduPilot Gazebo plugin to work with Ignition, as it was named at the time. And it's just a summary of the kind of major changes. So Gazebo Classic is called using sort of Gazebo, and the object that you want to launch as a world file. It's a XML file using the SDF format. And there's a new set of command line tools in Gazebo Garden. They're all prefixed with GZ, and then there's additional verbs. So sim launches the simulation, but there's also topics and services that you can call using the same command line set. And everything is just called a .sdf file now. The plugin, so the original plugin, there's links here to Pierre's original plugin, and we still kind of got maintenance support of that. And the new plugin, we've kind of moved under the ArduPilot org, and you can see the link there. There's changes in the way that the plugins are constructed. So in the previous version of Gazebo, you'd have plugin specific types of plugin according to whether you're working with a model or changing a GUI or something like that. In the new version, there's just a series of abstract interfaces which you attach to a general concept of a system plugin, and you implement the things that you want it to do. So the update system has changed a bit. There used to be just a single update, and now there's a 3-phase update step. So there's a pre-update where you would apply all the forces in your custom plugins. The main update step is where the physics engine itself time steps the equations of motion. And then there's a post-update step where you would query the results of the time stepping for sensor information and other things you might want to feed back into downstream state. So for example, the ArduPilot plugin acquires all the information about the pose, current accelerations and velocities, and ships them back to SITL. And it's a fairly abstract system to work with to start, but it's very powerful in that everything is a system. So once you have written a couple of plugins, it becomes quite clear that it's a much easier system to work with. The changes so there's quite a big change in the plugin, and that's all been migrated across now. In terms of running existing models and worlds that you may have, the big change, I think, is probably in the materials. So any previous models that used the Ogre scripts are not going to work in the new environment. So you may need to modify existing models to use either very simple materials or proper physically based rendering sort of sets of data where you provide things like the normal maps and the diffusion maps and bump maps and things like that to fully specify the way the thing's going to appear. And because everything's a plugin, it's a little bit more effort up front to configure the world. So previously, most of the systems that you'd want to have active when you ran the simulation would be available automatically. In the new setup, you have to enable them all with plugins. But once you've got an example set up, it's fairly easy to follow. We've used the JSON interface. We've retained the Sim Gazebo for the legacy version. The main differences are in that they both sort of receive a binary servo packet, but SimJSON has a versioned binary servo packet, and that's quite useful because we've been able to use that feature to upgrade the support to have 32 servos as well, and we'll discuss that a little bit later. The data that gets returned is now just a JSON package, as previously it was a binary state. So that means that it can be a lot of the fields can be optional. So some of the sensor state that gets returned is optional, and if it's in the package, then SIDL picks it up and starts passing it on to the appropriate backends. One of the main changes, and this is probably a theme that'll be going through in the way that you control, you translate the servo pulse width modulation data that comes from ArduPilot into commands that get used to control joints or various other bits and pieces within the simulation. So originally, ArduPilot would have its own controllers, the plugin for velocity or position control, and when you set up the model, you would specify whether you want a joint to be velocity or position controlled. So rotors, for example, would be velocity controlled, and then you'd have to assign the PID gains for those. But as we had a request from Clyde McQueen, who wanted to get his blue ROV simulation running using the new version of Gazebo. And so what we did is we forwarded the command straight through onto the Gazebo message bus. So there's a GZ topic layer. And so the changes are rather than try and apply the commands within our plugin, we just forward the command on. We may normalize it slightly and offset it, given kind of information about the offsets and multipliers. And then we specify a topic that we want this command to be directed to. That goes onto the ignition bus, and then it gets picked up by the appropriate plugin. In this case, we're targeting the thrusters plugin, which is something that a plugin that is provided as part of the Gazebo package. And so we configured the ROV to use the standard thrusters with Gazebo and just redirected all the servo packages through to that. So I think increasingly that's the way we're probably going to be using the plugin, is rather than actually controlling joints and positions specifically, we'll just forward the commands on to the appropriate plugins within the Gazebo packages. It's quite a nice example, this one, because it also uses the ROS bridge, and it's got a MAV-ROS2 connection. So if you're looking for an example of how to use Gazebo, MAV-ROS, and ROS2 with ArduPilot, then I'd recommend taking a look at Clyde's Blue ROV ignition example. So some other things we've added. There used to be a parachute. I don't know if there was previously a parachute plugin, but there is one now. So Alex Molchanov asked if we could get that working, and we worked with him to provide that. So that uses this feature where you can have detachable joints. And again, we're using the command technique. In this case, what we're doing is just triggering a release command. So when the servo goes high, the command release goes high. And there's a custom plugin in this case. And what happens there is that you specify link you want to attach the parachute to. There's a model, which is the parachute, and then there's a pose, so how you'd like that parachute to originally appear relative to the model when it gets deployed. And then there's the target topic that it's going to receive. And when that plugin receives a topic, it triggers the parachute and off it goes. So this is configured using the standard setup within ArduPilot, so it's parameter setup, and it works very nicely. So that's a new feature we've added to it. Okay, whoops, run ahead there. Another thing we've modified is that there's original versions of the plugin had facility for a camera and a gimbal to be attached to the Iris quadcopter. I upgraded that, so I gave it another degree of freedom. So the gimbal now is a little 2D gimbal with a camera attached. And previously there was a custom plugin within the ArduPilot package for dealing with the controller. But now we can just use one of the standard, well, actually two of the standard joint position controllers that are available. And again, we just forward the commands onto those, and the plugin delivered with part of the Gazebo packages are quite sufficient for moving those around. One of the nice things about doing that is that you can test it by sending the commands to the topics directly. So before you've got the CIL up and running, you can launch Gazebo, you can send topics to the commands to the topics to control in this case, the roll and tilt joints on the gimbal, and check everything's working properly. So by breaking the system up into having the plugin receive the servos from the sort of sim JSON backend, and then forward them back onto the transport layer, it makes testing the various parts of the model and the simulation a little bit easier, because you can break it up into testing the Gazebo joints, respond to all the commands you expect, and then you've got the mapping of the sort of commands coming from ArduPilot into the expected sort of ranges that you would like to have. Okay, so the nice thing about the JSON API is that it's extensible, and I haven't extended any of the fields that were there. So I've just used the ones that were provided but weren't populated. So we've added a facility for range sensors. So the JSON backend supports up to 6 range sensors. Now, there's many things that have been ported over from the classic version of Gazebo to the new version. The sonar sensors, unfortunately, are not included in that. However, we can proxy them using the GPU LiDAR sensor, and just limiting the scan beam width and range, and then attaching a number of those at various points on the model. You can feed those through into the JSON package that's returned back to CIL. And the configuration in ArduPilot is as standard and documented in the wiki. So we just set up the rangefinders from 1 to 6, specifying their poses relative to the frame, the body frame. And there's an additional set of fields that gets attached into the ArduPilot plugin XML package that just state the type of sensor, an index for which particular range slot you're going to target, and then again a topic, because the sensors will listen to information. The plugin will listen to information published by the sensors on the topic. So when you set a sensor up, you can specify what topic it's going to publish to, and the rate at which you want that sensor to publish. So sonar sensors in this case are being published at about 30 hertz. So that all works quite nicely, and you can see it all plumbed through into MAB proxy. So as the rover spins around, we can see the distance sensors hitting the wall and measuring them as you would hope. Another type of sensor, in this case we needed it for sailboats, is a wind vane or anemometer. So again, there's a slot available for that in JSON that we weren't using before. So in this case, it's not a sensor that's available in Gazebo. So we've written a custom sensor, and there's two parts to writing that. So you write a plugin that is the sensor itself, and then you write a system that basically monitors all of the anemometer sensors that you've added, and aggregates all of those results and makes those topics available for other systems to use. And the way we've tested that is that we've added the plugin to just a block, and set up the wind to be coming, in this case it's coming down the -y direction. And then as we spin the block around, we're using the sail plugin in Mav proxy, and we've configured the wind vane in parameters in ArduPilot to pick up the true and apparent wind. And as we spin the block around, we can see the data all flowing through nicely. So that's all working quite well. And we've got another set of sensors. And then the most recent thing we've changed is, so Buzz suggested we try attaching a whole set of rotors to a hexapod. And as it turns out, that's quite a straightforward thing to do in Gazebo. So it doesn't have the best aerodynamics, and we'll talk about that later, but it does have the ability to handle lots of quite complicated joints and structures. So it's an ideal simulation environment for prototyping this type of thing. But it's got a lot of servos. So the previous API supported up to 16 servos. To extend it, we added another servo packet into sim.json. There was a few other minor changes to make in order to be able to have the servo 32 enable parameter made available. And then what on the ArduPilot side, what happens is that if the servo 32 enable is set, then sim.json sends out the 32 channel packet, and if it's not, it sends out the 16 packet channel. So and the failback is to the previous behavior. They've got different magic numbers on them. So on the plugin side, we just needed to add an extra field to say if you have the 32 channels or not, and then you check to see whether you've got the right magic number on the servo packet as it comes through. So that's quite nice. Then we can have, in this case, we've got 6 rotors and then 16 leg actuators. There should really be 18, but at the moment, you can target up to 16 scripting channels. So in this particular case, there's a Lewis script handling the mixing and unfolding the legs. It's using the dynamic scripting matrix because at a later stage, we want to have a look at being able to alter the configuration of this thing while it's in flight. So at that point, the mixer will need to change at the same time. In this case, it's just replicating the hexacopter. And the 16 scripting channels are used to drive the leg servos. So that's a kind of nice example of doing that. But all of these things I think have now been folded into the master branch. Okay. Right. So there's a few tools. Now these are not as part of the ArduPilot package, but we may kind of get them upstreamed or incorporated either into Gazebo or somewhere else. So the first one is force visualization. So with all of these plugins, you can modify the simulation to add plugins that apply different types of forces. So in this case, we're looking at a set of different types of sails. We've got wing sails with elevators, or soft sails, and we're writing a custom set of lift and drag plugins to deal with the forces that we'd expect these to experience in the presence of wind. But there are many other plugins active at the same time, and so if you want to try and attribute the particular set of forces arising from a plugin to the resultant behavior of the system, it's quite useful to be able to switch the forces on and see them, and it was quite useful for doing this. So this is a visualization plugin. It's an example of how you can extend the GUI to subscribe to information that has been sent around the simulation, and add extra visualization as well. This was used to verify that the lift and drag were correctly aligned with the incident wind and the appropriate sort of link frames of the sails. The way it works is that the GUI plugin itself has access to the entity component system. It gets an update. You can query that for information, including forces that you may have published from other systems. Another tool, and this is something I wrote. I wrote a set of Python bindings for two of the libraries. So GZ Transport uses 0MQ for shifting all the data around, and the messages it sends are Google protobuffers, and there's two libraries to handle this. And the Gazebo sim doesn't provide bindings for these in Python, but actually, if you have access to the messages, you can control most of the simulation. So rather than write a series of bindings against all the objects and simulation objects and things like that, you can do a great deal by just having accesses to the messages and access to the transport layer directly. So here's an example where all the controllers, and mentioned earlier that these position controllers have PID gains, having to tune those, and you generally do need to tune each one within a simulation. It's very time consuming if you have to go back and edit the XML, restart your simulation, relaunch it every time. So you can write a service on the joint itself, which will subscribe to, which will respond to an input message. And in this case, not shown here, but complementary to this is the controller has a service which allows you to set the PID gains. And then you can write Python scripts to target it directly. And what's quite nice about the fact that they're protobuffers is that you've got a native mapping through from the sort of natural bindings provided by the Google protobuffer libraries into GZ's transport using two binding libraries, and these are pybind11 and pybind11 protobuf. And it all just works. So you can declare all your messages in Python. You create an instance of the transport layer in Python, and you just construct the objects. The callbacks, so they are, you've got like the C++ transport layer calling the Python callbacks and returning the messages. So it works as you would want it to work, and all the binding and marshalling just happens under the hood. So that's quite nice, and hopefully we can get this upstreamed into Gazebo. So sort of talking to the team that are looking after the GZ transport layer at the moment, and they seem quite open to adopting this approach. They're going to change it around as suits them, but I think the principle of having a Python binding layer to the message and transport layer is something that is quite useful. Where it's handy is there is a bridge. So the ROS GZ bridge does do a similar thing. It's a series of C++ libraries. However, if you wish to get a new type of data shipped into ROS, you need to modify that library. and provide the mappings for that. And there are many things. The set of things that you might be interested querying the simulation directly is much larger than the set of standard messages that you'd put through onto a ROS bus. So if you just want to quickly go in and plot some data or control the simulation or modify it somehow, having a direct Python binding to the simulation layer is very, very useful. So there's a library for that, and I mean, I've certainly found it quite useful in putting together simulations and testing. Okay, so there's a bit of a intermediate next steps here before moving on to some models examples. So this is a quite extensive wish list of things that would be nice to have, and lay out a potential program forward. So there are quite a few sensors available now in the standard Gazebo simulation package: altimeters, air pressure, airspeed, batteries, many cameras, magnetometers, and NavSat. So the question is like, what's the best approach to integrate these additional sensors into the simulation? So we can get the data out of Gazebo, we can map it into whatever form we like. I don't think all of this data should be going back through the JSON payload, but the question is, what's the best way? So that's really something I need to follow up with the dev team, and I think there's maybe some of the work with the ROS2 layer, it could go through that, or there may be other methods of mapping it through. But I'm not sure how to best approach this, but there's additional information it would be nice to be able to pull back from the simulation and forward on into SITL. On the environment side, this is probably more on the Gazebo side than the ArduPilot side. So these sensors need to have sensible environments in which to monitor, and they're fairly simple at the moment. So you've got these various vector or scalar fields that you can specify, and I think there's room for improvement on the Gazebo side in order to set these up. There's some open questions. So the component system doesn't currently specify an order in which the updates occur. So everything that's a system that has a pre-update method gets lumped into one schedule. And you can't really control at the moment whether you update things like the wind and the waves before you update all the things that need to measure them and then apply them in the physics step. So you're not really guaranteed that the environment will be updated prior to the physics system that's using it. So I think there's some scope for improvement there. Things like the wind effects and system updates, they do a couple of things. They update the field, and they also apply the results of those fields to the various links. And I think they should probably be separate. So you have a set of systems that updates the environment, and then you have a set of systems that queries that and applies it. Where they are coupled, it's quite hard to get into the information that you need. So that could change. So there's some things that could be improved there, and then you could have different ways of you could have quite complex systems for modifying the environments and then sensor sets to feed them back into the controllers. On the physics side, so Gazebo is not a great aerodynamics simulator. It has a model for lift and drag. It's very simple. It has piecewise linear lift and drag coefficient curves, which you can get to sort of work, but I think there are lots of effects that are not really accurately modeled. So there's a question of like, how can you improve them? There's three different methods of providing thrust for quadcopters. There's two main ones. You can either control a joint velocity and then apply lift and drag to the rotors, or there's a dedicated model for doing that. Now they have slightly different interfaces, and so they're a little bit different to get to. It'd be nice to homogenize those, and I think there's some work to do that. And there's other tooling around the kind of these models which would make them easier to use. So being able to replicate thrust and torque curves, or just specify those and have the models created to match them, would be very useful. There's some discussion in a PX4 discussion group about suggestions of perhaps the multi-copter model could be reparameterized to make it easier to set up. I've noticed that in the approach that we've generally used in ArduPilot joint velocity with the lift drag plugins, there's some stability issues using that for particular models where the Swan K1, it just about works with it. I mean, it does work, but it's not great. The Omnicopter, I cannot get to work with the driving lift and driving rotor lift and drag by spinning a prop and then calculating the aerodynamic forces on it directly. So there's something funny going on there. So generally improving that would, improve the behavior and accuracy of the aircraft. For rovers and boats, as we'll come on to, I think the modeling is getting pretty good. So it's not specifically a aerodynamics environment, but and a very speculative thing, if that was something that people wanted to do, then you do have the facility to replace the entire physics system as a plugin. So, with a great deal of work, you could replace the plugin library with an aerodynamics library such as JSB Sim. You could have the proper Earth-centered inertial coordinates. You could do all of that. It's very far from clear whether that's an undertaking that's worth taking on. Something else that would be quite useful is being able to abstract the joint position and velocity controllers behind servo and speed controller components. That wrapped up all the PID tuning, made it easier to configure to a physical spec, and added battery usage and that type of thing. So really you have a model, you attach kind of servos and speed controllers to it as you would expect, and you just then plumb the pulse width modulation kind of commands forwarded from ArduPilot straight through into those, and you try and make it easy to set up. At the moment, it's quite time consuming to set up each of these controllers properly, because different vehicles, they have different inertials, they require different PID controllers for each of the joint or velocity controllers. So making that easier would make it a easier process to set up new models and get them running properly. There we are. Okay, so that's really the work that's been done on the plugins and the system side, and then we also have a number of example models as well to use with all of this. So in addition to the Iris quadcopter and Zephyr that was provided with the original plugin, we've put a bunch of stuff into CITL models to use different features and provide platforms, the starter models for people who might want to use the simulation for testing things. So example, we can have custom rover frames. So this is example of Roger Chen's Sawpp rover. So it's a Curiosity style rover. It's got 10 joints, it's got 6 wheels, four of them are steerable. It's quite nice because it can do in-place steering, which makes it amenable for the BROS2 SLAM nav2 packages. It's a Lewis scripted motor mixer. So it uses some of the nice new features available within ArduPilot for scripting, and applies them to models which are quite nicely specified in Gazebo. Another example is for marine simulation, and a bit more on that later. This is just like a simple buoy bot type model, PVC tubes with a couple of thrusters on them. So it's essentially a skid steer rover. There's quite a lot of physics going on. So there's the wave modeling for the environment. There's a set of hydrodynamics being applied to each of the hulls. and we're set up with, like, in this case, there's a sensor package on it, includes the inertial measurement unit, which is essential for getting the ArduPilot integration, but we've also got a magnetometer, camera, and a navsat attached to it as well. So these are all working quite nicely, and we can add these packages into Civil models as we go. And then things that are already available, a selection of quad planes. One of the quadrupeds that was done as a GSOC project. We kind of took that and put the model into Gazebo. There's some environments and some rovers and some experimental craft as well. So it's pretty flexible in what you can put together. I think targeting rovers or multi-vehicle type simulations, or things that are a little bit odd and don't kind of fit somewhere else, Gazebo is quite flexible for taking those on. Okay, and then the last thing is, this is kind of back to putting all of these pieces in place to properly port the original Sailboat model over so that it works correctly in Gazebo now with all the new features. So this model is based off a Racing Sparrow 750. So the designer, Brian Hever, was very kind, gave me permission to use his CAD model and make that available. So I've scaled it up slightly in the model. It's supposed to be 750 millimeters. It's actually double that size in the simulation. But it's quite a nice model to work with. So the approach for this is that the first thing you need to do is to make all the visuals and collisions available. So Blender's the tool for that. So the visuals in Gazebo are like either STL or Collada files, and so Gazebo is a good tool for exporting those. The collision mesh for the marine simulations needs to be cleaned up, because the physics is applied to the mesh directly. So each triangle has it's determined whether it's currently below the waterline or on the waterline. Triangles get cut if they're on the waterline, and then the hydrodynamics forces get applied to each triangle. So the mesh needs to be clean. You need to have as fewer triangles as possible to make it run real time, but not so few that you lose the essentials of the shape. So there's a bit of work there to tidy it up, and that's part of the preparing the model. The physics system itself, there's three main things going on. There's hydrodynamics, so that has a hydrostatic buoyancy. There's a couple of drag forces that are applied. There's a viscous drag, and there's a sort of pressure type drag that are applied normally to each element. You can see in the diagram, the green area is the current submersed area. So that's where the forces are applied. That's changing as the waves are changing and the boat's moving. So all of that's getting recalculated. And then we've got two lift systems, one for the foils, for the fin and the rudder, and then a lift system for the sails. As mentioned before, we added an wind vane anemometer goes through. So the green circle in the dial is a top-down view. We've got like a sensor on the top of the mast. There's there's transforms to put that into the side of the kind of the FRD body frame that ArduPilot's expecting. And then we've just got some checks using the sail module in MavProxy to make sure that the apparent and true wind is coming from the directions that we expect it to. The sails themselves, they need a custom controller, because you want the sail to be able to, if you haven't sheeted it in tightly, you want it to lie to the wind. So it's a type of joint position controller, but in this case, you only apply the force when the actual angle is the absolute value of the angle you want is less than the actual angle. So you pull the thing into its target position, but you don't kind of apply any force if it overshoots. So that naturally lets the sail just, if it's not sheeted, it'll lie to the wind, and as you sheet it, it kind of comes into the center line. But it also means that when the boat tacks, the sail comes across correctly, and you don't have to control that. And then finally, there's the plugin itself. So we've used this command forwarding technique. So there's commands are forwarded on to the rudder and sails, and autonomous sailing is set with the sail enable flag and the parameter set, and it all comes together. So yeah, and then that's kind of the speed run through it. So there's a video to play, and if there's any questions, it may be a bit hard for me to hear because I'm remote, but yeah.
All right, can you hear me there, Rhys?
I can, yes.
Great, okay. I think I will need to relay questions from the audience. It might be hard to get the microphone to go through to you otherwise. So, questions from the audience? Yes, Rishabh.
Do you think I should just unmute?
Yes, you can unmute there. Yes, indeed, and I'll mute here.
Hey, Rhys, can you hear me?
Yes. Oh, not now, sorry.
Rhys, you need to mute while Rishabh unmutes to ask questions. Okay, great. Rishabh, you can unmute.
Rhys, can you hear me?
All right, so what's the question, Rishabh?
So I wanted to ask him about the camera APIs, like how do you access the camera on, say, a Python script? And I also wanted to ask him, okay, just first question. Yeah.
Okay, so he wants to ask about the relaying of cameras via Gazebo. So can we get input from camera systems? I'm guessing computer vision type applications. So if you wanted to do visual odometry or avoidance applications, how would you pipe through the video data to be able to process those with a Python script at some point?
Right. Yeah. So there's two approaches, I think. So you can, so the ROS GZ layer has a mapping of the camera sensors through into the standard ROS image messages. So you could use that, or you could do it directly with the Python bridge layer that I've provided, or you could write a C++ plugin to do that. So there's a number of ways that you can get access to the messages. I think if you had tools that already processed them from the standard ROS image messages, then the bridge is probably the way to go. But that puts a dependency on ROS2 for your system. So it really depends on whether you want to do that or not.
Is because they have firstly a really neat API to access it nicely and easily, but also that the camera is you can modify the parameters so they kind of really closely match your existing camera that you might be using on a hardware.
Right.
Is that possible on the simulation?
So Rishabh's saying that is his experience with AirSim, he could modify the camera characteristics, presumably the extrinsics of the camera, to match a real camera that he's working with. Is it possible to modify camera properties to match a real camera?
That they are configurable. I mean, you would need to have a look at the camera sensors that Gazebo provides and see whether they have enough fields for you to manage. And so if the custom camera, if the current range of cameras, they do have things you can control the field of view, you can control the kind of various properties of the camera. It's sort of field of view, aspect ratio, pixel count, and things like that. I think if it didn't provide exactly what you wanted, then you'd have the option of writing a custom plugin to modify, to provide your own camera sensor, or modify one of the existing ones as you require. So the whole system is configurable, and I think that's kind of one of the powerful things about Gazebo, is that they've moved everything as a plugin. So if you don't have exactly the sensor that you require, then it's an option to write it yourself. And they've made integrating sensors into this sort of custom sensors into the simulation much easier. It used to be quite difficult to do that. It's much easier to add a custom sensor now than it was before.
Last question, also from Rhys.
Yeah. So how easy is it? So for example, if I want to place an April tag, or a moving human, or just whatever, it's like a custom object inside the environment. Is it like really tough to do?
All right. So asking about adding custom objects inside the environment, such as an April tag. If you want to place that in the environment so that your camera can see it, you can do vision applications with that April tag. How easy it is to do something like that?
Yeah, I think so. I mean, there are many examples. I mean, that part of Gazebo hasn't fundamentally changed from the earlier versions. I mean, what's happened on the objects is that the ability to render them has got better, but the whole ability to place objects and models within the environment is much the same. So I think there are probably many examples of tagged objects. So if you did a search for April tags in Gazebo, and I think Shiv used that in one of the docking examples. So I think most of that transfers through. There are quite rich environments that have been provided examples. I think on the opening page, there was an example with the Sawpp challenge where they created a cave system as one of the DARPA challenges, which has many objects, quite a complicated map. So I think that's possible. Doing that efficiently, I think, requires a bit of scripting rather than constructing the worlds by hand, but I think it's possible to do that, yeah.
Okay, well, I think that's all we have time for. That was absolutely fantastic, Rhys. Thank you so much. And